This is your presenter Asloob Mudassar, and I am presenting slide number 90 of the course on laser physics. Question is, discuss the effect of a limiting aperture in a symmetric and a non-symmetric resonator. How are the eigensolutions, that is fields, computed in this case? The answer is, the finite aperture in a two-mirror resonant cavity can be achieved either by using mirrors of finite limiting aperture. The second case is by inserting a circular diaphragm of limiting size in the cavity. The third option is by using an active medium of limiting transverse dimensions. Use of limiting aperture of any type will give rise to diffraction losses, and the propagating field will also be modified. For example, a propagating Gaussian field in the presence of limiting aperture will not be strictly Gaussian. Let us use a finite aperture by assuming mirrors of finite limiting sizes. Consider a two-mirror symmetric resonator. For the symmetric resonator, we have the two radii of curvature which are equal to each other and equal to capital R in this case. That is, R1 is equal to R2 is equal to capital R. And then A1 is equal to A2 is equal to A, where A1 and A2 are explained in the next figure. So consider a two-mirror symmetric resonator shown in figure 90.1 with its equivalent lens guide structure shown in figure number 2. So this is the setup that we are going to discuss now. The caption is a typical two-mirror symmetric resonator, because we have the same mirrors with the same radii of curvature equal to capital R, and the dimensions of the two mirrors are also the same, that is equal to 2a, and 2a is actually the limiting aperture of each mirror, and the two mirrors are separated by a resonator length equal to capital L, and both mirrors are spherical in nature. The figure explains them. And its equivalent lens guide diagram is shown in figure over here. The caption is lens guide geometry equivalent to the geometry shown in figure number 1. You can see that it consists of two lenses, lens 1 and lens 2. The aperture sizes of the lenses are shown, which are equal to 2a in both cases, and the optic axis or the z axis passing through the center of these lenses is also shown. Perpendicular to the z-axis, we have the transverse directions, in which we have the x and y coordinates as the transverse plane to the z-axis. The focal length of each lens, which are equal to each other, is related to the radii of curvature through the relationship, that is f1 is equal to capital R by 2. Capital L is the separation between the two lenses. Okay. The field in the cavity will reproduce in shape after traversing a distance equal to capital L, and thus can be given by the integral. That is the sigma prime times E prime of xy0 is equal to the double integral, both with the limits from minus a to plus a, and then we have kappa of xy, x1, y1, and then we have E prime of x1, y1, 0, and dx1 and dy1. So you see that this is the field that we have written. And here we have used the word. The field in the cavity will reproduce in shape after traversing a distance equal to L. You see that in the previous, for the detail of this integral, I would suggest you consult slide number 83, where the derivation and this integral has been discussed in much greater detail. And there you see that that the field will reproduce in shape. There we have discussed that the field would reproduce in shape after traversing a distance equal to 2L. But here we are talking about that the field will reproduce in shape after traversing a distance equal to capital L, because we have a symmetric resonator. That is, for example, look at its lens guide diagram. So if we consider a field, if we consider a point just before the lens 1, then you see that the field will pass through lens 1, and then the field will travel a distance equal to capital L towards the lens 2, and just before the lens 2, the one pass of the resonator is complete, because after that the symmetric condition will arise. That is, the light will pass through lens 2, and then of course it will cover a distance equal to capital L. The things will repeat itself, and you see that this repetition will occur after traversing a distance equal to capital L. So we are assuming that the field just before the lens 1 should reproduce it just before the lens 2, because after that the things are going to repeat. As in case of one round trip, the field repeats itself. So that's why here in this particular case of the symmetric resonator, we have the condition that the field will repeat after traversing a distance equal to capital L. So that's why we have written down a field over here. Now, for this one, as I suggested, you consult slide number 83. But now I am going to give you a brief discussion about this equation number 1 in using appendix. So let's go to the appendix and see a brief view of this derivation. E prime of x1, y1, 0 is the field at the diaphragm 1. That is just before the lens, or just after the mirror 1. That is at z is equal to 0. So this is the field which is at the diaphragm 1, or at the location of z is equal to 0. The corresponding field at z is equal to capital L plane, that is just before the lens 2 or just before the mirror 2. The field is given by E prime as a function of x, y, capital L is equal to e to the power minus kl double integral over the lens 1 over the diaphragm of the lens 1, and then integrand contains E prime of x1, y1, 0, which is the initial field at the location of z is equal to 0, multiplied by the kappa of x, y, x1, y1, and the integrand variables are dx1 and dy1. Kappa is actually the propagation kernel. Assume that the input field, here we are assuming, as we have done in case of in the slide number 83, we have assumed for the solution of this integral that the input field is a point source represented by a delta function. So we are not going in that detail. So let's move forward. Assume that in the given geometry the field is reproduced in shape after one round trip. And here one round trip mean that is from z is equal to 0 to z is equal to capital L. That is just before the lens 1 to just before the lens 2. That will form a one round trip, because after that the field will reproduce itself. And the field at that point, that is just before the lens 2, is represented by E prime of x, y, L, and that is equal to sigma prime e to the power minus iota kl, then multiplied by E prime of x, y, 0, where sigma prime is equal to mod of sigma multiplied by e to the power iota 5. This is by definition of the complex number. That is, a complex quantity can be represented by its magnitude multiplied by its phase factor. So this is a complex constant, and sigma mod of sigma prime is less than 0 is due to the loss in the beam due to diffraction. Again, for the detail of this one, have a look at the presentation number 83. Now substituting E prime of x, y, L from equation number A2 into equation number A1. So we are using equation number A2 into equation number A1, because the left hand side, you see that I have marked it with red, and also the left hand side of equation 1 marked with red. So eliminating E prime of x comma y L with the equation number 2, between equation number A1 and A2 we get this quantity, that is sigma prime of E prime of x is sigma prime multiplied by the E prime of xy0 is equal to the double integral over the surface over the aperture of lens 1. Then the integral contains E prime of x1 y1 0, where E prime of x1 y1 0 is the field at the aperture 1, and then kappa and the kappa as a function of xy x1 y1, and the variables of the integrals are dx1 and dy1. Note that the derivation of these equations for the derivation of these equations you should consult question number 83, that is the slide number 83. So you see that this is the equation that I am referring. So I have given you a brief introduction about the derivation of this integral of this equation, and you see that here this is the equation that I am just talking about. So this is the field after one round trip of the cavity, that is from the distance z is equal to 0 to distance z is equal to capital L. Equation number 83.6, for this one you can also consult, for example, for equation number 1 you can consult equation number 83.6, where x1 y1 is defined as on the transverse plane located at z is equal to 0, and xy is defined on the plane z is equal to capital L, and kappa will be the same as for free space propagation and is given by kappa is equal to iota over d times lambda e to the power minus iota k, and within the parentheses we have a times x1 square plus y1 square plus d times x square plus y square minus 2x1 x minus 2y1 y divided by 2 times capital B, where a b c d, you see that C is not appearing over here, but A, B, C, D is a matrix for the one round trip, that is for the distance from just before the lens 1 to the distance just before the lens 2. So for this one, you can consult equation number 86.5. The ABCD matrix is given by. So if you look at the diagram below, you can formulate the ABCD matrix for one round trip, because that includes traversing the lens and then traversing the free space distance equal to capital L. So the lens matrix is given by 1 minus 1 over f1, then 0 and 1. This is the matrix of the lens 1, and then the free space propagation is represented by the matrix 1 capital L 0 and 1. So the product of these two will give you the ABCD matrix, and this ABCD matrix is for the one round trip, that is for the distance z is equal to 0, that is from the location of the lens 1 to just before the location of lens 2. If the limiting aperture is present, the eigen solutions E prime of x comma y comma 0 will not be equal to the product of Hermite polynomials and a Gaussian function. You see that we have discussed in equation in some of the previous slides that if the limiting apertures are not present, that is we have infinite sizes of the lenses 1 and 2, and we have also the infinite sizes of the mirrors 1 and 2. In that case, we found that the solution of such a wave can be represented in terms of the Hermite polynomials and also the product with Gaussian function. But you see that if in case of a limiting aperture, as we are discussing now, the eigen solutions, that is E prime of x comma y comma 0 will not be equal to the product of the Hermite polynomials and a Gaussian function. The analytical solution of the integral in equation number 1, that is this integral, the analytical solution of this integral is not possible. Iterative solution is worked out on a computer by first assuming an expression for E prime of x1, y1 and 0. That is, we shall assume that the initial field just before the lens 1 or just after the mirror 1 is known. and then obtaining a solution E prime of x comma y comma L. That is the solution just before the lens 2. This will be obtained through an iterative process or through the solution of the integral. The integral is solved for E prime of x comma y comma 2L by using E prime of x1 y1 0 is equal to E prime of x comma y comma L. So you see that first of all you will use E prime of x1 y1 01 as the input in the integral, and then you will solve the integral iteratively for the value of E prime of x comma y comma L, and then you will use this as an input to the integral, and then you will solve the integral for the next value of which will be E prime of x comma y comma 2L. So you see that in this way you can solve the integral iteratively. And this is the case when you have the limiting apertures present in the resonator. The analytical solution will not be possible, and only the iterative solutions of the integral number 1, that is this integral, will be possible. Okay. In the third step, the integral is solved for E prime of x comma y comma 3L, because then E prime of x comma y comma 2L will be used as an input to the integral, and the right hand side of the integral, which will be E prime of x comma y comma 3L, will be solved by using that is by setting E prime of x1 y1 comma 0 equal to E prime of x comma y comma 2L. And then of course we can solve that integral for the next value, which is E prime of x comma y comma 3L. The iterative process is repeated till the field does not change except in amplitude, which decreases due to diffraction losses, and except the phase factor, which accounts the propagation length in successive iterative steps. So the amplitude and the phase factor could change for the values of these E prime values, that is E prime of x comma y comma 1L, E prime of x comma y comma 2L, E prime of x comma y comma 3L. The expression of the fields will be the same, but the values of the amplitude and the phase factors will be modified because the amplitude will decrease according to the diffraction losses, and the phase factor will take care of the propagation length in the successive iterative processes. Except these two quantities, the rest of the quantities will be the same. So now let's discuss a typical two-mirror non-symmetric resonator. So see that here we are going to discuss non-symmetric resonator. You see that the spherical mirror 1 has a radius of curvature R1. The spherical mirror 2 has a radius of curvature R2. That is, the two mirrors have different radii of curvature. It means that we are discussing non-symmetric resonator. Separated by the two mirrors are separated by distance equal to capital L, and the apertures of the two mirrors, that is the apertures of the mirror 1 and 2, are respectively 2A1 and 2A2. Before that, we have discussed this geometry in one of our previous slides, assuming that 2A1 is of infinite size and 2A2 of infinite sizes. But here we are limiting the size of these mirrors to a value of 2A1 and to a value of 2A2 respectively. And it is a non-symmetric resonator because the two mirrors are of different radii of curvature. So this is what we are now going to discuss this one. Next, we consider non-symmetric two-mirror resonator shown in figure number 3 with its equivalent lens guide structure shown in figure number 4. So let me discuss the lens guide structure equivalent to figure number 3, which is over here. So you can see that I have lens 1, then I have lens 2, then I have lens 1. So this will form a complete one round trip from lens 1 to lens 1. And the lens 1 has a focal length f1, which is equal to r1 by 2. Lens 2 has a focal length f2, which is equal to r2 by 2. And again, the lens 1 on the right hand side has a focal length equal to f1. The apertures of the lens 1 on the left hand side and on the right hand side are equal to 2a1, and the aperture of the lens 2 is 2a2. The separation between the lens 1 and lens 2 is capital L, and similarly the separation from lens 2 to lens 1 on the right hand side is also equal to capital L. This is the lens guide geometry equivalent to the geometry shown in figure number 3. So you see that we can use this geometry for the purpose of calculations. The field E prime of x1, y1, 0 on the x1, y1 plane at z is equal to 0 is related to the field E prime of x2, y2 capital L at z is equal to capital L through the integral. So you see that from point 1 to point 2 we can calculate the integral which is given by this one. So E prime of x2, y2 capital L, that is the field just before the just at the plane of the lens 2 is equal to e to the power minus iota kl, and the integral is over the diaphragm of the lens 1. Then we have the kappa 1 2, which is the propagation kernel. Kappa 1 2 contains is the function of x2 y2 comma x1 y1, and then we have the initial field at the lens aperture 1, which is e prime of x1 y1 and 0, and of course the integral variables are dx1 and dy1. So kappa 1 2 is the beam propagation kernel from z is equal to 0 to z is equal to capital L. The field E prime x of x2 y2 capital L on the x2 y2 plane, which is located at z is equal to capital L, that is at the plane of the lens 2, is related to the field E prime of x3 y3 2L on the x3 y3 plane, which is located at z is equal to 2L through the integral. So you see that the coordinate at the transverse coordinate at the location of the lens 1 is x1 y1. At the location of the lens 2, the transverse coordinates are x2 y2. Transverse means it is perpendicular to the z direction, which is the z direction is the direction through which the passing through the center of these lenses, and the coordinate at the lens 1 on the rightmost side is x3 and y3. So the field at the location of the lens 1 on the rightmost side is given by equation number 4, which is E prime of x3 y3 2L is equal to e to the power minus iota kl, and the integral variables are on the diaphragm of the lens 2, and we have the propagation kernel kappa 21. Kappa 21 mean from lens 2 to lens 1, and this is the function of x3 y3 and comma x2 y2, and E prime, which is the field at the lens 2 coordinate at the lens 2 transverse plane, which is x2 y2 capital L, and of course here the integral variables are dx2 and dy2. So you see that in equation number 3 and 4 I have shown two quantities which are in red, which means that I can substitute the value of the field from equation number 3 on the left hand side to the field on the integral in equation number 4 on the right hand side, and then we shall get the integral which is shown in equation number 5. But before that, let me explain that kappa 21 is the beam propagation kernel from z is equal to capital L to z is equal to 2L. That is a propagation from the lens 2 to the lens 1 on the right hand side. Substituting E prime of x2 y2 L in the last integral from the integral in equation number 3, we obtain. So we have E prime of x3 y3 2L, which is the field on the lens 1 located on the right hand side is equal to e to the power minus iota 2k capital L and the double integral is over the surface of the lens 1. It contains kappa of x as a kappa with variables x3 y3 comma x1 y1, and then E prime, which is the initial field at the location of the lens 1, which is E prime of x1 y1 0, and then the integral variables are dx1 and dy1. So it means that we have used the value of that integral over here, and we have introduced. You see that when you substitute this value from equation number 3 over in equation number 4, then of course you will get the field on the right hand side, which is the E prime of x3 y3 to L. But you see that that would contain the integral number 1 and also the integral over the surface 2. That is the integral over length surface and the 1 and the integral over the length surface 2. But you see that here we define kappa 3. We will define kappa, which is as a function of x3, y3, x1 and y1 in the following form, where the propagation kernel kappa of as a function of x3, y3, x1 and y1 from z is equal to 0 to z is equal to 2L is given by. So you see that the kappa in equation number 3, in equation number 5 is now given by kappa as a variable of x3, y3, x1, y1 is equal to double integral on the length surface 2 contains kappa 2, 1 of x3, y3, x2, y2 and kappa 1, 2, which is a function of x2, y2, x1 and y1, and the integral variables is dx2 and dy2. So you see that this field, this is the field after one round trip is given in equation number 5 with kappa contained in the integral on the right hand side is given by equation number 6. So evaluate kappa in equation number 6 first and then substitute that kappa in equation number 5 to solve the integral in equation number 5 to get the field on the right hand side, which is E prime of x3, y3 and 2L. So the integral in equation number 5 along with the integral in equation number 6 are first attempted for analytic solution. So you see that when we substitute, first of all, we try to find out the solution of equation number 6 in terms of kappa through analytical means. If analytical expression is possible, then well and good. But if analytical solution is not possible, then of course we shall attempt the iterative method. The analytical method will be preferred. So analytically, we shall solve equation number 6 and then we shall substitute the value of kappa in equation number 5 and then we shall solve equation number 5 analytically. But if the solution of equation number 6 in for kappa is not possible analytically, we shall attempt the iterative solution of this equation, and then of course kappa will be substituted in equation number 5 and which will again give you the iterative solution of the field on the left hand side in equation number 5. So the integral in equation number 5 along with the integral in equation number 6 are first attempted for analytical solution if possible. Otherwise, iterative method is applied. So you see that I have given the solutions for two cavities. That is for the symmetric case. This one is the symmetric case. And I have discussed the solutions for this resonator with the help of its lens equivalent diagram, lens guide diagram or lens guide geometry, and then I have discussed this geometry, which is a two mirror geometry with a non-symmetric resonator, and with the help of its lens guide geometry I have given its solution, which is shown in equation number 5 and 6. So this solves, this gives the answer to the questions that we have posed in our presentation. So this is the end of slide number 90.